Hello, my name is Daniel Winklener. I'm a research scientist at MIT, and today I will tell you about high current H2 plus beams from compact cyclotrons using a novel RFQ Direct Injection. Before going into the cyclotron design, I want to give you a brief motivation of why we are interested in building this machine. And this is the ISODAR project, a definitive search for sterile neutrinos. After that, we'll talk about the details of the high current cyclotron design and how we used machine learning to optimize the RFQ mechanical parameters. In the standard model, we know of 3 neutrinos. These are part of the lepton-weak doublets, and they only interact through the weak force carried by the Z and the W boson. They can only be observed indirectly through their lepton partners, the electron, the mu, and the tau, hence the names of the neutrinos, muon neutrino, tau neutrino, electron neutrino. Now these neutrinos, originally assumed massless, actually do carry a small mass, and they oscillate, which is a very peculiar behavior. They can change their flavor state while they travel through space and time. This has been observed in many experiments over the past decades. 2 famous ones are the first observation in 1998 by Super K, and then a very nice observation by Camlin that is shown here in the bottom plot, where you can actually see the oscillation probability as an oscillation wave as a function of distance traveled over energy of the neutrinos. Now, these oscillations are not the only anomalies that we're seeing. There are additional excesses and deficits in some of the neutrino experiments that cannot be explained so far. But one possible explanation, or one candidate for an explanation, is the addition of another sterile neutrino, a neutrino that does not interact through the weak force, but it does participate in the oscillation. And here on the bottom, you can see a plot by the LSND experiment, which was one of the first to observe anomalies that could be possibly explained by a sterile neutrino. And there are many experiments out there that are trying to find these sterile neutrinos, but none of them are definitive. So the ISODAR experiment actually proposes a definitive search. That means within 5 years, we can say beyond 5 sigma whether or not there is a sterile neutrino or not. The way this is done is by putting a very intense electron antineutrino source close to a kiloton scale liquid scintillator detector. And here on the left, you can see a cartoonish picture of the YEMI lab facility. This is in South Korea, and it's a laboratory that is currently building a liquid scintillator detector. And if ISODAR is paired with this 3 kiloton liquid scintillator detector, then we would see a signal like this on the top right here, where we plot the survival probability of electron antineutrinos produced in our neutrino production target as a function of L over E, the distance traveled over the energy of the neutrinos. And you can see a very nice oscillation shape or oscillation wiggle here that is a smoking gun signature for the existence of a sterile neutrino. Now, if you take these measurements and you put them in context with global fit data, you can see that we are sensitive to a very large space here in this delta m squared, that's the mass splitting, and the sine square 2 theta, which is the mixing angle. And you can see here indicated earlier and very new global fits for allowed regions where these sterile neutrinos could live. And you can also see that YEMI lab with ISODAR would cover this region very nicely. Now the question is now, how do we actually produce enough electron antineutrinos to get the necessary statistics to provide a definitive experiment? And the answer is by building a new type of cyclotron. What we need is about 10 to the 23 neutrinos over 5 years. That's a very large number. And this translates into about 10 milliamperes of 60 MeV protons that are needed on target at 80% duty factor. And we're talking CW beams here. This also translates into about 600 kilowatts of beam power on target. This is a very hot target, and we have a group at Columbia University and University of Michigan who are working on the development of this target. This is not part of the presentation, of course. We have shown, however, that we can build a cyclotron providing these 10 milliamperes of 60 MeV protons, and we have shown this through calculation, experiment, and simulation. Cyclotrons, in our opinion, are the best suited accelerator for this purpose. partly because they can be built very compact for underground installation, and partly because they have been around for a long time and are well understood and can be quite cost-effective. The state of the art in high current cyclotrons is twofold. On one side, we have the commercial machines that are mostly used for medical isotope production. They can be built very compact and deliver about 1 milliampere of maximum beam current. On the other hand, we have PSI Injector 2, which is a research machine that has a record of 2.7 milliamperes of protons. This is about a factor 4 lower than what we need for ISODAR. PSI Injector 2 is also a 4-sector machine. That means it is larger than a compact cyclotron and doesn't lend itself as easily for underground installation. We have taken lessons from both of these accelerators and put them together and added some innovations of our own to design a record beam current of 10 milliamperes. This is the ISODAR cyclotron. It's a room temperature isochronous cyclotron operating in CW at 80% duty factor. It comes with 4 double gap RF cavities leading to high energy gain per turn. And in addition, I've highlighted this in blue here, we are using 3 novel ideas to improve the performance of this cyclotron. 1, we are accelerating H2+ instead of protons. I will talk about this on the next slide. 2, we are injecting directly axially through an RFQ embedded in the cyclotron yoke, which leads to very high bunching before injecting through the spiral reflector. And 3, we're utilizing vortex motion, an interesting beam dynamics effect that happens in space charge-dominated beams in isochronous machines. Let's talk about H2+ first, the molecular hydrogen ions. They are 2 protons bound together with 1 electron. This reduces the accelerated beam current by a factor of 2. So instead of 10 milliamperes of protons, we only need to accelerate 5 milliamperes of H2+. Once the particle beam has been accelerated and extracted from the cyclotron, we use a carbon stripping foil to remove the electron and get our proton beam back. Having a lower total current helps during the Levitt and during injection through the spiral reflector. Of course, it also comes with a bit of a drawback. As the H2+ is heavier than the protons, the higher magnetic rigidity leads to a slightly larger machine and to a slightly larger spiral reflector that we need to inject the beam into the cyclotron. But these are engineering challenges that we have addressed in the ISODAR design. Now, this H2+ beam has to be produced somewhere, of course, and for this we have built a new filament-driven multicusp ion source called MISC-1 at MIT. We have recently commissioned the ion source at 25% power, and I'm listing some highlights of the commissioning process here. We've seen over a milliamp of H2+ beam. We have seen a fraction of H2+ of over 80%. This is also shown in the plot on the top right here, where you can see the protons, the H2+ and the H3+ in a mass spectrum. And we have seen low emittances of 0.05 millimeter-milliwatt. We are now in the process of commissioning the source at 100%. After the ion source, the beam is transferred to the RFQ. Please note that there is a separate poster on the Levitt and matching to the RFQ by Lloyd Waits. I've noted this on the bottom of the slide here. The RFQ has multiple purposes. One is, of course, to transfer the beam efficiently to the center of the cyclotron. RFQs are really good at that. And secondly, and most importantly, the RFQ bunches the beam very aggressively, and this will lead to fewer beam losses in the center of the cyclotron later on. RFQs also accelerate, and so we're using it to accelerate the beam moderately from 15 to 70 keV, and they will sort out, and the RFQ will actually sort out some of the proton contamination of the beam. An RFQ in general is a set of 4 rods or vanes that are connected to an alternating voltage source. This leads to a continuous transverse focusing effect. And if we machine modulations onto these rods or vanes, then we can also get an additional longitudinal electric field component, which leads to bunching and acceleration. Here I'm showing a simulation that was done with the highly accurate particle in cell code warp. Warp is being developed at Lawrence Berkeley National Lab and is pretty well established. And what you can see here is that the beam is coming from the left. It is a continuous stream of particles, so this is a full 3D simulation. No assumptions are made about the bunching ab initio. The beam comes in from the left, and then you can see how it is bunched over time. And at 1.35 meters, it has reached the shortest length. This is where the RFQ ends. Right after that, you can see that the beam starts diverging, both in the transverse direction and in the longitudinal direction. And for this, we need to add additional focusing elements to counter this. We need to add additional focusing elements after the RFQ. And we, of course, need to bring the RFQ exit as close as possible to the center of the cyclotron so that the cyclotron can take over with the focusing as soon as possible. We have subcontracted the design and manufacturing of the RFQ to the company Beavertech in Germany. And on the next slides, I will point out some posters with details of the RFQ design. I will also highlight some parameters here. First of all, we're running the RFQ at 32.8 MHz, matching the cyclotron frequency. At the same time, the RFQ has to have a very small diameter because we want to embed it inside the cyclotron yoke. This pairing of small diameter and low frequency lends itself well to a split coaxial RFQ design, where the vanes are not attached to the tank walls radially, but they're actually pairwise attached to the entrance and exit flange, as indicated in the CAD drawing here. Other parameters of our RFQ are that the length is about 1.4 meters, the transmission rate is over 95%, and we have very good admittances of 40 kV degrees longitudinal and 0.35 degrees millimeter millirad transversally. We also have very low power consumption, and this is because we are not using the RFQ as an accelerator, but mainly as a buncher. I should point out that in our optimization process, we have actually reached better admittances by now. These are the baseline values, but the latest are actually about 30 kV degrees longitudinal and 0.25 millimeter millirad transverse. And this was done using machine learning, and there will be another poster on this pointed out later on. These are the posters pertaining to the RFQ design. The first one is the one that I mentioned previously. It's by Holger Höltermann about the RFQ technical design. The second one is by Daniel Kosa about the RFQ thermal simulations, where we showed very good agreement between CST and COMSOL and showed that the frequency detuning of the RFQ due to heating of the vanes is well within the capabilities of our plunger tuner. And then third, we have a poster about the optimization of the loop coupler that brings the power into the RFQ, where we looked at the positioning, the size, shape of the loop, and also the rotation. And all of these together show that this RFQ design is feasible, and we will commence the manufacturing in the near future. The optimized RFQ parameters were obtained using a machine learning technique. Here we first parameterized the RFQ cell parameters to reduce the number of input parameters, and then we use those parameterizations to create RFQs that are simulated using the standard tools like ParmTech, RFQ Gen, Warp, and TraceWin. And from this we obtain a large sample set. This sample set is then used to train and create a surrogate model. We do this either through polynomial chaos expansion or by using a neural net. The surrogate model has the advantage that it executes much faster than the original simulation tools. And by much, I mean orders of magnitude faster. And so we can then do multi-objective optimization very quickly to find the final optimized RFQ parameters. These final parameters are validated by running them through the original simulation tools again to make sure that the solution is really viable. And on this, we have another poster that is also presented by Daniel Koser, and I encourage you to look at it and ask him questions about the process. After being bunched and pre-accelerated, the beam is transferred onto the cyclotron median plane through an electrostatic quadrupole and a set of spiral inflector electrodes. These are spiral-shaped electrodes that create an electric field that, in combination with the cyclotron magnetic field, guide the beam onto the median plane and into its circular orbit. We have recently upgraded the Opal code to actually be able to very accurately simulate this process, including mirror charge and space charge and particle termination on the electrodes. And we are now in the process of simulating the RFQ output beam as it goes through this system and into the cyclotron. That means that the cyclotron simulations that I'm going to show on the next few slides are not yet using the RFQ beam. We did use twist parameters that are close to what we see, but we don't have a full start-to-end simulation as of this point. Just as a small caveat. Now that the beam is injected, we want to see vortex motion happen during the acceleration process. Vortex motion is the interplay between the beam's space charge forces and the external focusing forces of the isochronous cyclotron. This effect was first seen at PSI injector 2, and I have put a reference down here to a paper that compares OPAL simulations with measurements at this particle accelerator, with very good agreement. And I also placed a plot from this paper here, where you can see that an initially mismatched beam that is elongated will start twisting, vortexing if you will, and after several turns has reached a stable round distribution. Now, this round distribution will not change much in size anymore as it is being accelerated in the cyclotron and will lead to clean extraction with an electrostatic septum. One thing to point out here is that this is in the beam's local frame, which moves with the beam along the spiral trajectory. Here I'm now showing the OPAL simulations of the isodar cyclotron design. We again start with a mismatched beam that is slightly elongated in the longitudinal transverse space, and then we track it for 7 turns with space charge and the cyclotron's own focusing forces. And you can see that a slightly roundish distribution does develop, however, with a lot of halo around the beam. Now this halo would fill the space, the gaps between subsequent turns in the extraction region. So what we do is we carefully place collimators in the first few turns below 1.5 MeV, where the beam will not activate the cyclotron. And then we scrape away these halo particles, and the result of this you can see in the bottom right plot, where you see a round distribution with no halo, and this beam can now be accelerated to 60 MeV per nucleon, giving very few particles in the space between turns, leading to very clean extraction. And this is shown here. This is the same simulation as before, except we're now plotting the last 3 turns after the beam has reached 60 MeV per nucleon. You can see where we insert the 0.5 mm thick extraction septa, and the beam losses on these septa are below 50 watts. This is a factor 4 lower than what PSI injector 2 has determined as the limit for hands-on maintenance due to the activation of the material from the beam. You can also see that we can smoothly increase the turn separation with the help of the negatively charged electrodes on the outside of the beam, up to the point where we can insert the magnetic extraction channels. We stop the simulation at 135 degrees azimuth, indicated here with a black line saying final beam parameters, and the final beam parameters at this spot are listed on the left. We have recently put forward a publication on this, and I've indicated the archive number on the bottom of the slide. As an aside, we actually have a prototype experiment currently under construction to demonstrate RFQ Direct Injection into a compact cyclotron. This will be done with a 1 MeV test cyclotron that is depicted here in this CAD rendering on the right, opposite of the full 60 MeV isodar cyclotron. Before I conclude, I would like to point out that there are many more applications for high current cyclotrons like this. One of them being, for example, the production of medical isotopes. Another one, if you add another cyclotron to the chain that boosts the beam to 800 MeV, would be CP violation in the neutrino sector, or demonstrations for accelerator-driven systems and accelerator-driven subcritical reactors. And we do have another poster on these further applications presented by Lloyd Waits. In conclusion, ISODAR promises a rich physics program and has a mature design, both for the compact cyclotron and the target producing the electron antineutrinos. We have demonstrated these through experiments, particle in cell simulations, and computational fluid dynamics and finite elements analysis. And we also have several prototypes on the way. The ion source is already built, and the test cyclotron with RFQ Direct Injection is currently in the technical design phase and will be built soon. I hope I have piqued your interest, and I encourage you to look at all the posters and all the references that I've placed throughout the slides. The references are summarized again here. And with this, on behalf of the ISODAR collaboration and myself, I would like to say thank you for your attention, And please drop by during the Q&A session to ask all the questions that you might have.